but before moving further, I just want to ask again the question. All right, so today I talked about the necessity and also unnecessity of a couple of the brain areas, right? Like first one was about cerebellum, no, the brainstem, which may or may not give you the ability to move your body and hand and your legs and so on in the locked-in syndrome while keeping consciousness intact. And then cerebellum, 80% of the neurons in your brain. And then prefrontal cortex, that is important and significant for your social interaction and also decision-making personality. And then posterior visual areas that supports for your phenomenology of seeing. Now, Fu thinks that if you have only one side of the hemisphere, left only or right only, do you think you can still have a consciousness or not? So option A is that if you have a left hemisphere, yeah, you are conscious. Option B is that yes, if I have a right side of the brain, then I'm conscious. And the other option is that no, you can't be conscious if you have only one hemisphere. What's your opinion? Not conscious if only one. So that means that you need at least two hemispheres to have consciousness. Okay. So again, option A is that if you have a left hemisphere, you are conscious. If you have a right hemisphere, you are conscious. That's option B. And then other is you can't be conscious if you don't have at least to some extent on both sides. Okay, so the most popular is the option A, and the B and the others are more or less the same. Let's move on. So this is quite striking in the sense of all of these options. In fact, this was a really rare case that was reported in 2000 in Lancet. Lancet is probably the best and most significant kind of the medical journal in the world. And this is the report of one person, 44 years old, civil servant. So he's actually functioning, and he has, I think, a child as well, and IQ of 75. So he's not, definitely normal range. Normal range is 100, and 75 means that the 2 standard deviation lower and so on. But verbal IQ wise, it's 84, meaning that he is quite, capable of communicating, and also, no issue in terms of interpreting and also asking for questions and so on. And this is a case of the hydrocephalus, meaning that this black part of the brain is filled with the cerebral spinal fluid, CSF. And this is looking at the brain from the coronal slice, horizontally from around this level. And then B is a slice that goes sort of from the top to the bottom. And then again, you don't see much thing here. And then this is a part of the subcortical areas and the fourth ventricle. And this is the eyes and the nose, and then this is entire brain. Again, almost nothing is there. But from this, and until he was scanned like this, he didn't notice that he was like that actually. This is quite striking case, but it seems like quite a bit of the brain areas are potentially not necessary in the brain if the lesion happens in the early part of your life. And then also another striking case is this. These are the 6 high functioning hemispherectomy patients who are studied in Iowa and published a couple of years ago. And then here, I think the left is left here and the right is right. So regardless of the left, whether you lose left side or right side, it's almost complete loss here, for example, on the right hemisphere, and the complete loss for the left hemisphere here, and then quite a bit here on the left side. In all of them, the subjects were highly conscious. And it's hard to believe, but most of them, so if you are diagnosed with some types of epilepsy, and then if the epilepsy starts across many different areas on one side and then spread into the other side, this hemispherectomy is sometimes operated. And then long-term recovery and so on has been discussed in this paper. But in some cases of the subjects, roughly like 10% or 20%, they can function without any assistance. And I think, if I remember correctly, 20% of the kids can go to the normal school without any support. And many of them eventually become adults with normal functioning kind of jobs, almost like this person. But here, because of the surgery, everybody in this population knows that I don't have half of the brain, okay? But they can actually recover. And one of the clue of why they can actually function almost like normal is that their brain's connections become strengthened. So here is the measure called functional connectivity. It's a sort of the interaction between the brain areas. Now they quantified how strongly it is interacting with others. And in the case of the control people, like most of us who have two brain hemispheres, like the areas in the frontal areas and the temporal areas and the parietal areas, like they are interacting, but it's much less compared to the hemispherectomized people. So their frontal and temporal and the occipital, they interact strongly, here. You see that, color indicates the strength of the, functional connectivity. And it's, in general, it's more stronger here and then here as well. So even if you don't have strong, the huge number of neurons and those areas of the brain, it may be possible to compensate for that kind of the deficit and then to support consciousness through right kind of the configuration of the connections. And that may be also consistent with the idea of this integrated information. Integration through the areas are more important than the mere presence of a bunch of neurons, just a simple measure of the complexity. These hemispherectomized people are connected in a very tightly and coherent manner within one hemisphere to support the complex consciousness. So far, fine. Is there any questions about them? Okay, let's move on. So now the next question is that is an experience of a blind side seeing something similar to something very faintly. So task to probe blind side phenomenology is to test whether their phenomenology is like seeing something faint or not. And the issue is, these types of the behavior in the GY, like maybe GY fluctuates in terms of the reporting, criteria. So phenomenology itself is always the same, and that may result in this good behavior performance. But he may feel like, oh yes, I want to say that I can see it now, but not in other cases. So that would be a problematic, but that's actually possible. So we want to know how to do it, how it feels like. So the way they tested was something like this. So again, you show a stimulus briefly while subjects are fixating at the center. So you can't move your eyes, okay? And then presented the stimulus either on intact side with a different kind of contrast or a blind side with different location and different contrast. Okay. And then in this case, so in this particular case, sorry, I made a mistake. So within the intact hemisphere, they presented 4 types of the stimulus. So, top left, top right, and bottom left and bottom right. And all of them are very faint, 3% contrast. And then sometimes in one case, on the right side, a blind hemisphere, and then a different level of the contrast stimulus, 30%, 45%, 99%. And then if they thought that they didn't see anything, they could choose pressing this button or this button to report that, no, I didn't see anything. Okay, so there are 6 alternatives to choose one of the 4 locations. 1, 2, 3, 4, or 5. That's so the location of the blind field, or 6 to report that I didn't see anything. Clear? Okay, so far I think it's fine. And then first experiment consisted of 60% of the faint stimulus and high contrast in the blind for 5% and the no stimulus in 35%. And then the result is that the 60% case of the faint stimulus all correctly localized. So when people were the blind side subject was able to touch the location of the thing. And then when stimulus was not presented in this 35% of the trials, then he also said that no, I didn't see anything, and so no false alarm. In the case of the high contrast stimulus, if 30% or 40% stimulus was presented, then he said no, I didn't see it. And then in the case of 99% stimulus, he said yes, actually I saw it. So depending on the contrast of the stimulus, in this case, he changed the report of the stimulus on the blind spot. To quantify something like that, we need to start to think about how to quantify the degree of conscious seeing. And it's a kind of a complicated things called signal detection theory. But an important thing for you to learn, which is very simple, is to have a distinction between presence or absence of the stimulus, and then response yes or no by the subject. And then this creates 2x2 table. If stimulus is present, and then people say yes, I saw, it's called a hit. And if they say no, then it's called a miss. And then on the other hand, when the stimulus is not there, but they said yes, then it's called a false alarm, and then no stimulus, and then no report, it's called a correct rejection. Okay, so this 4-way categorization is very important, and I may ask you in the e-assessment. So to come back to this, high contrast stimulus and no stimulus in the case of experiment 1, here there was no false alarm, because in the case when no stimulus was there, that participant said that I don't see it, so there was no false alarm or correct rejection. But when there was a stimulus in high contrast, stimulus in the blind field, here 30 or 40% stimulus, there was no hit. Then 99% stimulus, all hit. And so for each case of a stimulus, we can compute the signal detection theory variable. And complicated things into aside, this is called receiver operating characteristic. Receiver operating characteristic curves, ROC curve. And what it tries to plot is that on the x-axis, it is the rate of the false alarm, and the y-axis is a hit. So in the case of this, no 30% or 45% stimulus, because there was a 0% false alarm and 0% hit, it locates here. Okay. And then in the case of the 99% contrast stimulus, 0% false alarm, but 100% hit, so it was here. And in the units of the D prime, so-called D prime, it's called saturating fall, and area under the curve it's 1. But in this case, it's kind of ambiguous because all the three other cases are possible. So that's how we can start to quantify the signal detection measure in the blindsided patient. So in summary, blindsided patient GY accurately and normally report faint stimulus in their intact field. And when no stimulus is presented, GY can report seeing nothing. GY reported not seeing for 30 or 40% contrast stimuli, and GY reported 99% high contrast stimuli. And so it's possible that GY have an abnormal detection criterion, but with this only, it's not possible to answer. Okay. So do you have any questions so far? What was the D prime in the graph before? Okay, so good point. So here, I skipped this explanation. So thanks for asking. D prime is a measure of the separation between the two distributions. So under the ideal situation where you have a, like Gaussian distribution here and another Gaussian distribution here, and if the width of the so-called standard deviation, did you guys learn standard deviation in the statistics class or other class? Yes or no? Maybe should I do the poll? It's in high school, yes, okay. So this is called a Gaussian or normal distribution, and the width of this is called standard deviation. If it looks like this, then it has a very small standard deviation, and if it's like this, then it's a large standard deviation, okay? And then when your response is distributed along, x-axis, and under the stimulus present situation, your brain response, for example, locates or distributes like this. And then under the stimulus absence, your brain response locates like this. If the peak of this Gaussian is separated in the same size as this the width of the Gaussian, then that's called a D prime of 1. It's one unit of the separation. And then notice that if there is only 1 unit of the separation, there is a mistake here, right? Here, if your criterion of the response to say yes, I saw it at this optimum location, even though the stimulus itself was absent, you make a mistake at this location, and that's called a false alarm. And there's another mistake category here. Can anyone type in what's it's called? This part. Even though when the stimulus was present, because it was below the criteria, people say, no, I didn't see it. There was a description in the last slide. Yes, miss. It's called a miss. Great. Sort of nice. So this, if the distribution is overlapping, then you make a mistake in terms of false alarm or miss. And that's quantified with this, ROC curve. So here, this optimum line corresponds to this diagonal line around here. And then this means that, okay, so you have like 30% of the false alarm and also 30% of the miss. And that's why you are here. And if you have a distribution like this, D prime 2, twice as wide as separated here. This is a D prime 2 situation. Then mistake is, much smaller here and then here. Like 10% false alarm and also only 15% miss. So this way, you can take a look at whether the patient is saying always no or yes, depending on the criterion. Just to explain, I'll just explain. This is quite important. So, okay. And then with that, I'll finish today's lecture. So, for example, if there is a person who says always yes, because he has a lower criterion here, right? Yes, always. Then there's no mistake in terms of the miss, because all the present stimulus trial was, reported as yes, I saw it, right? On the other hand, your mistake in terms of false alarm increases a lot. So this is a false alarm. And how does it correspond to? Is this D prime 2 line, but moving towards this location. Or maybe around here, actually. So now the hit rate is 100%, right? But the false alarm increases up to like 60%. This is just fake figure, so you can't trust my thing. But the D prime 2 corresponds to this, and then changing the criterion shifts from here to here. So this what I meant by this 0% false alarm, 0% hit for 30% or 45% stimulus, and how it actually relates to the criterion is that so far this explanation is fine. Does it make sense so far? If that's the case, then I'll just go yes, okay, sort of. Let me know which one is unclear. Maybe I'll just ask you as a sort of a question. So the problem of this outcome, 0% false alarm and 0% hit, is that it is compatible with D prime 0 or 1 or 2 or 3 or 4 even. So we can't say whether this patient was actually able to discriminate, but have a super conservative criterion. Let's say if this is a absent and this is a present, and then he just say yes only to the right. In this case, everything is miss and everything is correct rejection. So it results in here. So to distinguish this situation into 0 or 1 or 2 or 3 of the discriminability, what do you think is necessary? Can anybody type in a chat box? Or should I just ask another poll, maybe? So maybe, what should I say? You need a new data point. Yes, so that's great. So how can you generate a new data point? That's the question. If you can come up with that, then that's almost like thinking about something like this will be very important for your final project, actually. The key point here is to change your criteria, right? Maybe this person wanted to say yes only when signal is way too strong. And then here, this criterion corresponds to he just doesn't want to say yes. So what's the way to manipulate the probability that people say yes or no? Can you propose any ways to manipulate the way to people to say yes or no? Changing the contrast, that's one way. But the problem of the changing contrast is that with respect to one particular contrast, I want to see this. If the changing the contrast change from this distribution into this distribution, then it just changes the D prime itself, right? Does it make sense? D prime is measuring the separation between the distribution. What we want to change is the criterion of the response. Any idea? So then maybe I'll just say the answer. It's a potentially, reward, right? If you give a reward or punishment in a way that changes this yes and no, then people can move the criterion, and that's sometimes done in psychology. If you let's say so this 2x2 table, saying no, saying yes, and then present and absent. If you give let's say $1 for yes and present, whereas if you give if you penalize -1 $1 for saying yes for the absent trials, then that will give you incentive to move back your criterion here, right? So in general, changing the reward structure changes the way you respond to the stimulus. And ideally, giving a reward and a punishment moderates the performance in an optimum way. Electrical shock on the wrong answer. That's also another great way of doing it. So that basically corresponds to punishing this part and then this part. So punishing wrong or rewarding correct changes this criterion from here to here. That's quite important. Correct, Suleiman. Great. So is there any other comments or questions today? Otherwise, then that's it for today. Okay, and in case you're interested in this last part, what it's like to be a blindside, a higher criterion for detection, this is a bit more complicated. So there is a YouTube link to this topic here, and I'll put this link in the slide. You don't need to watch it, but if you're interested, you can watch it. All right. So for now, I'll just, okay, but there was another question. Actually, if you have time, could you go over the blindside experiment one more time? And the 6 AFC one, okay? So experimental procedure-wise, this one, right? So here, it's important to understand that in any given trial, okay, so this figure is a bit confusing in the sense that it shows all the possibility, but each of the trial, okay, each of the trial subjects fixating here, and then it's either the brief presentation of something here or something here. Make sense so far? And then it's using different response option. And each trial, after each trial, you can move into, move your response into this way or this way or this way or this way or so on. So that's the part of the 6AFC choice, 6 alternative choice. Okay, so far fine. All right. Then there was a manipulation in terms of proportion of the stimulus presented, and that's 30 or 60%, 5%, 35%. That's fine as well. Okay. And then this is the results basically. So when it's presented in a faint stimulus, so 60% of points were faint, right? Yes. Yes. And the percentage-wise, it may be a bit confusing to, think about it. Just think about it. 60 times now it was presented in one of the location. Maybe 15, 15, 15, 15. And all of them are faints. Yes. 3% contrast. This is a contrast, okay? All right. And then for the rest of the 35% of trials or 35 trials, they didn't show anything. And the 5% or 5 trials, they show it in here. Fine? Okay. And then this is the result of the 5%, within 5% trials. And then to quantify that, I introduced this, signal detection theory. But this part is the results. Makes sense? Okay, got it. Okay, is there any other question? Perfect, fine. Okay, then see you next week. And also, I think this week we don't have a tutorial. All right. See you. Thank you.